Yep, I am live on YouTube and am I live on Twitch? Yep, I am live on Twitch and okay, I am live on YouTube twice. That is also amazing. Now, machine modern assembly language, not machine language. Yep. Yesterday, where were we? We were on chapter number 5 and we had done sequencing, selection, and iteration. And now we had to move on to subroutines. And let's keep our goal for today to complete get all the exercises of subroutines. Let's see, and but if it comes that we have to sacrifice either the quality or our goal, we will sacrifice our goal. We will not sacrifice the quality for achieving our goal because the goal doesn't mean anything if we do not do it properly, right? We cannot half-ass this thing. We are not going to do it again and again. The times that we are going to do it, we have to do it completely and fully. Let's go. Subroutines, complex selection, yep, iteration, and then we have subroutines here. Okay. A subroutine is a sequence of instructions to perform a specific task, packaged as a single unit. Depending on the particular programming language, a subroutine may be called a procedure, a function, a routine, a method, a subprogram, or some other name. And all that means the same thing. Some languages, such as Pascal, make a distinction between functions and procedures. Okay, a function must return a value and must not alter its input arguments or have any other side effects, such as producing output or changing static or global variables. A procedure returns no value but may alter the value of its arguments or have other side effects. Okay. Other languages, such as C, make no distinction between procedures and functions. In these languages, functions may be described as pure or impure functions. A function is pure if it always returns the same output for the same input. That is, it does not depend on the context in which it is called. It always returns the same output for the same input. The function always evaluates the same result value when given the same arguments, and evaluation of the result does not cause any semantically observable side effects or outputs. And by side effects, they mean like printing something to the terminal or changing some state somewhere else. The first condition implies that the function result cannot depend on any hidden information or state that may change as program execution proceeds or between different executions of the program. The program nor can it the program executions of program, nor can it depend on any external inputs from input-output devices. The result value of a pure function does not depend on anything other than the argument values. If the function returns a multiple result values, then these two conditions must apply to all result values, otherwise the function is impure. Another way to state this is that impure functions have side effects while pure functions have no side effects. Assembly language does not impose any distinction between procedures and functions, pure or impure. The assembly language will provide a way to call subroutines and return from them. It is up to the programmer to decide how to pass arguments to the subroutines and how to pass return values back to the section of code that called the subroutine. Yes, that makes sense. Like we can specify which registers that subroutine uses to take its input and then which registers it gives it its output in. Generally, it starts from the zeroth register. Once again, the expert assembly programmer will use these structured programming concepts to write efficient, readable, debuggable, and maintainable code. Advantages of subroutines. Subroutines help programmers to design reliable programs by decomposing a large problem into a set of smaller problems. It is much easier to write and debug a set of small code pieces. Yes, that makes sense. Than it is to work on one large piece of code. Careful use of subroutines will often substantially reduce the cost of developing and maintaining a large program while increasing its quality and reliability. Makes sense? The advantages of breaking a program into subroutines include enabling reuse of code across multiple programs. Yes, I can call that subroutine across multiple programs, reducing duplicate code within a program. Yes, I don't have to repeat the code multiple times in a program, enabling the programming task to divide, enabling the programming task to be divided between several programmers or teams. Yes, makes sense. Like I can order or request people to write subroutines that perform specific things and then return some specific things based on the input parameters, decomposing a complex programming task into smaller steps that are easier to write, understand, and maintain, enabling the programming task to be divided into stages of development to match various stages of a project, hiding implementation details from users of the subroutine, a programming principle known as information hiding or black boxing. Disadvantages of subroutines. There are two major disadvantages to using subroutines. First, invoking a subroutine versus using an inline code imposes overhead. The arguments to subroutines must be put in some known location where the subroutine can find them. If the subroutine is a function, then the return value must be put into a known location where the caller can find it. Also, a subroutine typically requires some standard entry and exit code to manage the stack and save and restore and restore restore the return address like branch link. Okay, calling a subroutine adds an overhead compared to using some inline code. Why? Because the program counter has to be updated to point to the new instructions that are to be executed, and then the lines of code are executed instead of just being executed. In most languages, the cost of using subroutines is hidden from the programmer. In assembly, however, the programmer is often painfully aware of the cost since they have to explicitly write the entry and exit code for each subroutine and must explicitly write the instructions to pass the data into the subroutine. However, the advantages far outweigh the cost. Assembly programmers can get a very large and failure to modularize the code by using subroutines will result in code that cannot be understood or debugged, much less maintained and extended. However, the advantages far outweigh the cost. Assembly programs can get very large, and failure to modularize the code by using subroutines will result in code that cannot be understood or debugged, much less maintained or extended. Makes sense. Here is a C program. I have a thing called list1 which contains person D and another string which contains you enter this and then an integer. Then I scan F and then I scan F percent n stir one printf I scan F. Okay, I scan for a digit and store that into n, and then I print it here and then return with 0. C standard library functions. Subroutines may be defined within a program or a set of subroutines may be packaged together in a standard library. Libraries of subroutines may be used by multiple programs, and most languages provide some built-in library functions. The C language has a very large set of functions in the C standard library. All of the functions in the C standard library are available to any programmer program that has been linked with the C standard library. Link, linked, like the final task after you have an object or file after your assembler has done its magic. Even assembly programmers can make use of this library. Linking is done automatically when GCC GNU-C compiler is used to assemble the program source. All the programmer needs to know is the name of the function and how to pass parameters to it. The name of the function and how to pass parameters to it. Passing parameters listing 519. This thing, scanf and printf, shows a very simple C program which reads an integer from a standard input using scanf and prints the integer to standard output using printf. An equivalent program written in AArch64 assembly is shown in 520. These examples show how parameters can be passed to subroutines in C and equivalently in assembly language. Oh yeah, we will not see what is down there. We will write this on our own in assembly language. Let's do it. Um, I will take it here, and this also has to go here. And now, yep, lang. Yeah, this is my folder where I write my assembly code. Now, mm, print num.s. Here, first line, I need to have a string label which contains the string which I want to print using printf. You entered %b \n, and the symbol which ASCII is, which is %d. This symbol will be used by the scanf function. Now, inside the main text section, I have a global thing called main, and I also align stuff. And now I define the main label, which first stores the pair of registers 29 and register 30. Where does it store them? In the stack after incrementing, after pre-incrementing itself by 16 bits. That is making 16 bytes of storage in the stack and then storing them. And now what do I want to do? First, I want to call scanf, and scanf will take %d as its first argument and then number as the second argument. So I also would like to have a byte or 64 bytes, a label called num, which will point to a quad, which will store 0 initially. A quad means 8 bytes. Now I want to get the address of the quad in here in the 0th register. For that, I get the page address in the 0th register for the quad, and for that I do num %page and then add the offset to the 0th register for the page. Now in the 0th register I have the address of %d. No shit, would like to have this onto the stack. So before moving it onto the stack, let me put it here, over in over here. Mm, and then I want to put this onto the stack. Therefore, let me get some free space on the stack. How do I get space on the stack? I subtract from the stack some, let's say 16 bytes, and then I store the value in the first register, where at the top of the stack. Now I have the address of the number, and now in the zeroth register, I would like to have the address of %d, which can be done by what? ADRP, get the address of the page, sim page to get the page address, and then adding the offset for the symbol page offset. Now it should work. Now I'll so this will branch link to scanner, and after this I should have at in the num location the address, and in the num location the number that got printed, and yeah, all set. Now I want to call printf. For printf I have to provide two arguments. First the string this, and then this number quads address, and quads address will go onto the stack. Well, at the top of the stack I already have the quads address, so don't have to do anything there, I guess. And now I will get the address of the string here by first getting the page address and adding the page offset, and then I can just branch link printf. This should work, and then at this point everything is done. We can free the stack by adding to the stack pointer the number 16, and then load pair the original values of 29 and the 30th register that were there. Percent 16, and then at the end return. This should work, I guess. Length, length print nums, and output sub dot out. Okay, it wants me to enter a number. That does not make sense. Okay, am I accessing much more than I need? That is crazy. Uh, I think the problem is at this point I I have the wrong thing at the top of the stack. Let me put the right thing at the top of the stack. First, getting the address of the right thing, then actually getting the right thing by storing the contents of the first register at the top of the stack. Now clang and oh 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 wait. It wants address. I am providing. What am I providing here? Uh, yes, I am stupid. At this point, I'm using this to provide to store the address at the top of the stack. But I do not have to provide the address at the top of the stack. I have to provide the value that is at that address, not the address itself. So to get the value, I do LDR load into the first register the value whose address is stored at the first register, and then store the value that I got in the first register at the top of the stack. Now this should work, I guess. Hmm. Es funktioniert. It works. Yep, it does work. Now, C standard library. Yep. Passing argument. Yep. All processor families have their own standard methods. Processor families have their own standard methods or function call conventions, which specify how arguments are passed to subroutines and how function values are returned. The function call is standard. The function call standard allows programmers to write subroutines and uh, s- libraries of subroutines that can be called by other programmers. In most cases, the function calling standards are not enforced by hardware but by assembly programmers and compiler writers. Conform to the standards in order to make their code accessible to other programmers. The basic subroutine calling rules for the AArch64 processors are simple. The first eight parameters go in these registers, and any remaining parameters are pushed to the stack in reverse order. In reverse order, so that the first argument goes to the top of the stack, the second at below that, and the third argument below that. Okay, so they get a string 1, a string 2, and a number, which is a word that takes 32 bits integer. Yeah, right, that is the integer type in C that takes 32 bits. We used 64 bits to store, which is to store our number, which means we used a double to store our number. Now, we first store these, yep, and then we get the address of string 1 into the zeroth register, and then we get the address of n into the first register, then we call scanf, then we get the address of the second string that we want to print into the first register, then we get the address of the number of n into the first register, and then we get the value that the address at n stores into the first register. Then we call printf, and then we move 0 to the zeroth register to make it the return value with which the program returns. Then we uh, pop the frame pointer and the link register back from the stack. Then we return, and then we do dot size main equals to current address for this line minus the address for this instruction. Okay. If the subroutine returns a value, then the value is stored in zeroth register before the function returns to its caller. Calling a subroutine in AArch64 assembly usually requires several lines of code. The number of lines required depends on how many arguments the subroutine requires and where the data for those arguments are stored. Some variables may already be in the correct register. Others may need to be moved from one register to another. Still, others may need to be loaded from memory into a register or loaded and then stored to the stack. Careful programming is required to minimize the amount of work that must be done just to move the subroutine arguments into their required locations. Okay, the AArch64 register set was introduced in Chapter 3. Some registers have special purposes that are dictated by the hardware design. Others have special purposes that are dictated by the programming conventions. Programmers follow these conventions so that their subroutines are keep compatible with each other. These conventions are simply a set of rules how registers should be used. In AArch64 assembly, all the registers have alternate names that can be used to help remember the rules for using them. In Figure 5.1 shows an expanded view of the AArch64 registers, including their alternate names and conventional use. This, these, the program counter, the P state, the ELR exception link register hardware special. Then we have the stack pointer, which is a hardware special register. Then we have the zero register, which is also a hardware special register. We have here link register and frame pointer and procedure link register. Then at the top from 0 to 7, we have general purpose registers, which are argument registers, volatile, used to pass argument values into a subroutine and to return used used to pass argument values into a subroutine and to return a result value from a function. They may also be used to hold intermediate values within a subroutine. Caller assumes they will be modified. Okay, they will be modified from register 0 to the register 7. They can be modified in a subroutine. And wait a minute. Now, moving on. What do we have? Yes, the eighth register, which is called XR, due to some reason, is the Linux system call number, where we put the number of the syscall that we want to call, which is also volatile. That is, it will change after the procedure. Indirect result register. Then we have from ninth to 15th, call saved registers, volatile. Caller saved registers, volatile. Okay. IP0, IP1, and PR. What is PR register? Intra procedure call registers, volatile platform registers, callee saved registers. A subroutine must preserve or save and restores the content of these registers. Okay, that makes sense. If they are used, they must be pushed to the stack at the beginning of the subroutine and stored before returning. Okay, that makes sense. Frame pointer and this and this. Now, registers 0 to 7 are used for passing arguments to subroutines. When calling a subroutine, the first argument must be placed in x0, and the second in x1, and so on. Conversely, when writing a function, it is safe to assume the arguments have been placed in these registers by the caller. If the function accepts more than 8 arguments, then the additional arguments are passed using the stack, as will be explained in section 5.4.2, 5.4.5.2. Where is it? Uh, yep, the argument registers 0 to 7 are considered to be volatile because their contents may be changed whenever a subroutine is called. If the contents are needed for after the subroutine, then they must be saved either to a non-volatile register or to stack before the subroutine is called. Makes sense. Registers Wait, so at this point here, I am getting the address again, but due to my calculation, the top of the stack should not have changed. So if I, instead of doing this, loading the value in this, if I get this by doing this, I am getting the address uh, that I stored at the top of the stack back into the first register. And then now I have the address of num. Now I want to get the actual value of num in the first register whose address is stored in num. And then I can store that value at the top of the stack. This should also work. Let's see. It works. It works as function yet. Can change whenever sub registers 8 to 17 are used for holding local variables in a subroutine. Local variables in a subroutine. These registers are also considered to be volatile. Some of these registers are used for special purposes by the operating system and or compiler. From the perspective of the programmer who is writing a user level program, the special purpose are not important, but we will explain them briefly nonetheless. Register X is used when using the system call SVC instruction on the Linux operating system to specify which system call is being invoked. The interrupt procedure is scratch register. The interrupt procedure is scratch registers X16 and 17 are used by the C library when calling dynamically linked functions like malloc, calloc. If a If a subroutine does not call any C library functions then it can use 16 and 17 as extra registers to store local variables. If a C library function is called, it may change the contents of 16 and 17 registers. Therefore, if 16th and or 17th are being used to store local variables, then their contents should be saved to another register or to the stack before a C library function is called. This is called caller saved because the caller is responsible for saving the contents of the register and restoring them after a subroutine. Oh, oh, this is called caller saved because the caller is responsible for saving the contents of the registers before restoring them after a subroutine. Caller saved. These are volatile. These are caller saved registers. That is, the caller or the one who wrote the program. The interrupt procedure is scratch registers 16 and 17 are used by the C library when calling dynamically linked functions. If a subroutine does not call any C library, then it can use 16 and 17 as extra registers to store local variables. If a C library function is called, it may change the contents of 16 and 17. Therefore, if 16 and 17 are being used to store local variables, then their contents should be stored to another register or to the stack before a C library function is called. This is called caller saved because the caller is responsible for saving the contents of the registers and restoring them after a subroutine. Okay, so this means that the contents of these registers from 9 to 15 can change during a procedure call. Therefore, the caller, the person calling the function using branch, has to store the contents of these registers either onto the stack or into some non-volatile registers and then restore them after the procedure has done calling. Now, registers 19 and 228 can also be used for holding local variables. Can also be used for holding local variables. However, before using them, the subroutine must save their contents, usually on the stack, and their contents must be restored before the subroutine exits. These registers are called non-volatile because their contents will not be changed by a subroutine call. Well, their contents will be changed during a subroutine call, but before the subroutine call exits, their contents would have been restored by the subroutine. That is a convention, not by demand. That is just a convention. More precisely, the subroutine may use them, but it will restore their contents before it returns them. Just what I said. As mentioned in section 3.2.2, register 29 can also be referred to colloquially as the frame pointer because it is used by the C compiler to track the stack frame unless code is compiled using omit frame pointer command line option. This register must be called x29 in GNU. AArch64 code. What does GNU has to do with AArch64? Now calling subroutines. How do I call a subroutine? The stack pointer SP link register 30 and program counter along with the argument registers are all involved in performing subroutine calls. The calling subroutine must place arguments in the argument registers and possibly on the stack as well. Placing the arguments in their proper locations is known as marshalling. Marshalling the arguments. After marshalling the arguments means placing the arguments in their proper space. Court martial is a court for army in US, or I don't know if it is a general term. The calling subroutine executes the branch link instruction which will modify the program counter and link register. The BL instruction copies the contents of the program counter to the link register, then loads the program counter with the address of the first instruction in the subroutine that is being called. The CPU will then fetch and execute its next instruction from the address in the program counter, which is the first instruction of the subroutine that is being called. Okay, now what does marshalling mean? Well, I get what it means here, but what does the term marshalling in general mean? An officer who helps to organize or control a large public event. And marshalling means putting the contents, the arguments in their correct registers. Bro, the subroutine is not working correctly. Well, I wrote the subroutine correctly. You're just not marshalling it properly. Okay. Simple function call in C. Hello, printf. Now, the simple function call in Arch assembly get the address of the string in the zeroth register, then branch link to printf. Yo. Our first example of calling a function will involve the printf function from the C standard library. The printf function can be a bit confusing at first, but it is extremely useful and flexible function for printing formatted output. Printf formatted. Formatted means it ends by formatted means it ends by a formatted means it ends by a null string, I guess, or and it also has percent %d and other delimiters if they are called delimiters in between. Now, the first argument of the address is the address of the format string, which is a null terminated ASCII string. The printf function examines the format string to determine how many other arguments have been passed to it. The format string may include conversion specifiers which start with percent character. For each conversion, these are called conversion specifiers. For each conversion specifier, printf assumes that an argument has been passed in the correct register or location on the stack. Yes, the argument is retrieved, converted according to the specified format and printed. The %d specifier causes the matching argument to be printed as a single signed decimal number. Other specifiers include %x to print the matching argument as an integer in hexadecimal, and C character to print the matching argument as an ASCII character, and %s to print a null terminated string. I can just print a string like that. That is crazy. Let's try to do it after this. The integer specifiers can include an optional width and zero padding specification. For example, 8 will print an integer in hexadecimal using 8 characters. Any leading zeros will be printed as spaces. The format is string 0. It will also print an integer in hexadecimal using 8 characters, but in this case, any leading zeros will be printed as zeros. Similarly, 15D, uh, D, D can be used to print an integer in base 10 using 10 spaces. 10 in base 10 using spaces to pad the numbers up to 15 characters, while 015D will print an integer in base 10 using zeros to pad up the 15 characters. I can use print %s and print string.s. In the dot data section, I have stir1, which has an ASCII's. It stores in ASCII's format what this string. And the second string is %s, the new line. Okay, is ASCII. This is the second string. Let's see what happens. In the top text, I give global main and also I align at to. So now I define the main label, which first stores the link register like a good boy that it is, and the stack frame pointer and the link register at the top of the stack by pre-incrementing the stack by 16 bytes. Yes, I'm using -16 to get 16 bytes of space at stack. Now what do I want to do? I want to call printf, and I want to give the address of stir1 as the first argument. So I will get the address of the page and then stir1 at the rate page to get the page address, and then add to the zeros register the offset for that page. Right now I have the address for the first string. Now I need to get the address of the second string, and I will use the register number 1 to get that address, and then add the offset stir2 page of, right? But I have to provide that address at the top of the stack. So I need some space at the top of the stack. And to get some space at the top of the stack, I subtract from the stack some things. Right now, I can store that address, which is in the first register at the top of the stack. And then I can just branch link and call printf. And after that, I know the deal has been done. At this point, I can clear the stack by adding 16. That is what I took from it, and then load back the X29 and X30 register values which are stored in the stack in the start, and then just return now. This should work, I suppose. Print a string and the output is brought out, and it at least compiles, and it works. Das funktioniert. So what if I give a new line character at the end of, what if I give a new line character at the end of this thing? I think, okay, this one too, I'm predicting will be printed on the next line, and then I would have, yeah, that's it. This one too will be printed on the next line, and yeah, okay, this listing 2.1, listing 2.1. Where is listing 2.1? This listing 2.1 shows a call to printf in C. The printf function requires one argument but can accept more than one. In this case, there is only one argument, the format string. Since the format string contains no conversion specifiers, printf does not require any additional arguments. And listing 5.2 shows an equivalent listing 5.2 shows an equivalent call made in AArch64 assembly language. The single argument, the address of the format string, is loaded into R0 register 0 and in conformance with the AArch64 subroutine call convention. Yes, the first argument goes in the 0th register, and then a large function call in C. Okay, pretty large. I have two integers I and k storing value 120 and 122. Then in my main function, I have another integer called j, and then I printed this, and the results are I, j, and k, three digits with three values. I can do this in assembly. Pretty easy. I can, yes, I can give the values directly. Yeah, that would be good. 5.4.5.1. Passing arguments in registers, that is called marshalling. Listing 5.23. This shows a call to printf in C having four arguments. The format string is the first argument. The format string contains three conversion specifiers and is followed by three more arguments. Arguments are matched to conversion specifiers according to their positions. The type of each argument matches the type indicated in the conversion specifier here. %d means a digit, integer, a number, a decimal number, and I am giving a decimal number here, and is followed by this. Arguments are matched to conversion specifiers according to their positions. The type of each argument matches the type indicated in the conversion specifier. The first conversion specifier is applied to the second argument. The second conversion specifier is applied to the third argument, and the third is specifier is applied to the fourth argument. The percent %d conversion specifier indicates decimal. Indicate that the arguments are to be interpreted as integers and printed in base 10 decimal. Listing 5.24. Next shows an equivalent call made in AArch64 assembly language. The arguments are loaded in these registers in conformance with the AArch64 subroutine call. Let us write this function in assembly. Print nums and print nums. I don't need these. I can do that, and then I can go on. Now, what is the string that I want to get here? Yep. Stir which will store an ASCII value, that is the result is %d space %d space %d and then new line. Now I need to get the address for this thing in the zeroth register. So for that, I first get the page address like usual and page address of stir page and then add to the zeroth register the offset for page. Now I have the first argument loaded and I need to get some free space in a stack. And how much free space? I need to pass in 3 word lengths. That is how many bytes? The one word is 4 bytes. I need three, that is 12 bytes. Let me use 20 bytes. And to get 20 bytes of space in the stack pointer, I need to subtract from it 20. And then what can I do? I can load at the stack pointer. I need to load the first argument exactly at the stack pointer, which is I cannot give an immediate value. So first I have to get the values in the registers. Let's say this is the first is 1, 2, 3, 4, and then the second argument is going to be 2, 3, 4, 5, and the third argument is going to be percent 3, 4, 5, 6. And now I need to store them at the stack in order. LDR, or actually I can store the first two like that using pair. The contents of, oh wait, W, W, because I'm only using a word. So load one at the stack, load, yep, and then load the contents of second register at stack -4. This is, yes, this is good. This is good. This is what I want. And then load W3 also at the stack after subtracting 8. This should work. And then I just branch link to printf and then free the space in the stack that I used stack pointer by adding to stack pointer whatever I subtracted and then loading back. Okay, that should work. Lang print num. Yeah, it should be out. But okay. Wait, yeah, boss error, bus error. Why am I getting a bus error? Is it because I'm trying to store a 32-bit value through a bus that takes 64 bits? Is that it? Let's see. I, I'm going off the screen, I guess. Yes, I was going there off the screen. Now it is fine. Okay, 47. Still getting a bus error. This is not incrementing the stack pointer ever. This is just to get an address. Oh shit, stupid I am. I don't have to subtract, I have to add to get at a higher level in the stack. That is just the messy way that the stack works in and speed error. Uh, okay, and load. Ah, this is supposed to be store, 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 store. I am storing the value at the register to some place in the stack. Okay, okay, there is still some error. Ah, 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 ah. What's the problem here? Should I use the full rat of the registers? Hmm. Let's see what happens this with this. I expect to see error. Added. Hmm. Okay, I am at this point getting some storage, extra storage in the stack, and then here I'm moving some values in some registers, and then I'm storing those values onto the stack, then calling the printf function, and then at the end I'm adding to it. Bus error is caused because of this. Maybe before doing this, I can actually, what I can actually do is store the top, move into the 29th register the value at the stack pointer. Then I increment the stack, but the stack pointer still, the frame pointer still points at the original location of the stack. So I can use 20. I'm in deep waters here. X29, and by subtracting X29, literally very deep waters. But I'm stupid still. Shit. How much location do I need? How much? Let me just do it. Ah, shit. 32 bits. That is what I want to use. So let me use www www store, 32 bits. But these values are not at the top of the stack. These are relative to the frame pointer, right? I want these values to be at the top of the stack. I would like to have these values at the top of the stack. How can I do that? How? Let's see what this does. I think this will give an error. Let's just see. All right. Is it because of these, or I might be like literally very stupid and it might just be this, that I am using 8 bits and bytes here instead of what I should be using. Okay, mm, 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 mm. What does this do? Here I am mm, doing something with the frame pointer. I'm getting the top of the stack at into the frame pointer location, like exactly into the frame pointer location. The top, the address that is on top, the address of the top of the stack into the frame pointer. I should not use the frame pointer here because I want to store things at the top of the stack. Okay, and instead of subtracting, I have to add to store. Hmm, a stack grows downwards, so this value means I'm storing the value here, and then this next line means I'm storing the value after adding 8 to the stack. Here is the stack, here is the place that the stack points, and now I add 8, and this after 8 bytes I will start storing the value whatever is in the second register, and the same here after adding 16 to this place that is the stack points to currently, I add 16 to it and then start storing from this address which I get after adding 16 to it. I expect to see error, and I did. Do I need more space? Let's see. 32. Is that enough for you? That seems to be enough. That actually seems to be enough space. Now, mm, um, but I'm still getting a bus error. So printf, ah, then I have to subtract 32. So the the mistake was I was not getting asking for enough space into the stack to store all these values. That was the crime that I did. Keep that in mind. Always keep that in mind. Ask space more than what you need, or at least what you need. Don't under ask. So we did this, made this thing, and static means that this is only accessible in the file. Int means that this can be asked for outside the file. Listing 5.2 shows shows an equivalent as yep. As long as there are 8 or fewer arguments that must be passed, they can all fit in registers 0 to 7. But when there are more arguments, things become a little more complicated. Any remaining arguments must be passed on the stack, program stack. C's are must be taken on the stack. C's are must be taken to ensure that care how stupid I am. I'm reading this as C and then R. Care must be taken to ensure that the arguments are pushed to the stack in the proper order. Also, after the function call, the arguments must be removed from the stack so that the stack pointer is restored to its original value. The tricky part is that on AArch64 processor, the stack is only allowed to grow or shrink in 16 bytes increment. Okay, there are differences in the assembly language that is being taught in this book and the assembly language that I am writing. Passing arguments on the stack, listing 5.2.5.25 shows to call printf this word. Yep, what I did there. Listing 5.25 shows a call to printf in C having more than 8 arguments. The format is the first argument. The format string contains 10 conversion specifiers, which implies that the format string must be followed by 10 additional arguments. Arguments are attached are matched to conversion specifiers according to their position. The type of each argument match is the type indicated in the conversion specifier. The first conversion specifier is applied to the second argument. The second conversion specifier is applied to the third argument. The third conversion specifier is applied to the fourth argument, and so on. The %t conversion specifier indicates that the arguments are to be implemented as strings and printed in base 10. That is, D means decimal. These are the things, and these are the arguments. String 5.26 shows an equivalent call made in assembly AArch64 assembly language. Since there are equivalent arguments, the last three must be pushed to program stack. The arguments are loaded into W9 to 11 and then the arguments are stored on the stack in reverse order. Even though the parameters are 4 bytes each, they are pushed onto the stack using 8 bytes. The top 4 bytes are padding. Note that the equivalent argument is placed in the stack at the higher location than the ninth and 10th arguments. Note that the 11th argument is placed in a stack at a higher location than the ninth and the 10th argument. Line 10 decrements the stack pointer by 32 bytes, providing room for 4 8-byte double words. 8-byte double words. This is necessary because the AArch64 stack pointer must always be on a 16-byte boundary. Since we have 8-byte arguments to push to stack, we must allocate 32 bytes, rounding up to next 16-byte boundary. It is then stores X9 into register of the stack pointer and extend 8 bytes above that line 11 stores listing 5.26. Get the address. The 19th register has the address of the stack. Address of I is word. Stores the address at the top of the stack. Whatever was the value in the 19th, because it's supposed to be non-volatile and I have to get back the value that is stored in there. Okay, address. I get the address of I into 9 and then I get the address of format into 0. That is a good thing. And then I get the value this into 1 by adding to the address stored in the 19th register 4. Then I add 4, I add nothing, then I add 4, then I add 2, then I add 4, then I add 8, then 12, then 16, then 20, then 24 to get all of these values. Makes sense. Marshall parameters. After getting these values, I need to get the remaining values. This is I, J, K, L, M, N, O. These three have to be stored into the stack. Partial parameters on a stack in reverse order. Minus P, R bar, P, R bar, L, M, N, O, P. Load the value in ninth, 10th, and 11th register. Then add to the stack pointer minus 32 to get how many bytes? 32 bytes of storage. And 32 bytes of storage is quite a bit of storage because 8 bytes is one, and that is like 4 bytes of store. 64-bit storage. 464-bit memory locations here. And then I store the values 9, 10, 11 at the stack. Then I call printf and free from the stack the memory that I used and then return properly. Okay. Listing 5.27 shows the 11th argument. 10th and 9th argument can be pushed to the top of the stack using a store peer instruction and store instruction. This would be slightly more efficient than the code shown in 5.26. The 11th argument is loaded into W1. The 10th argument is loaded into W10, and the 9th argument is loaded into W9. Then the stir instruction is used to store W9 and W10 on the stack and adjust the stack pointer after W11 is stored on the stack. Note that they have been placed in reverse order. So first, I stored this by adding to the stack. That is, the last argument is at the top, and like the stack grows downwards, so it is very stupid. So at the bottom of the stack, we have this. Then at a place higher, we have the second argument. And then at a place higher, we have the last argument. We call this. Okay. Shows we get the values into the ninth, 10th, and 11th register. And then we can simultaneously store these two like this. We pre-increment and we get a stack pointer that points below. Like, let's say the stack pointer points to this. There is a memory location here, and the stack pointer points to this, just like this, this. We have a memory. This is our stack, and our stack pointer currently points here. And then what does these two lines do? Uh, this first line, it first increments the stack pointer by subtracting from it 32. After subtracting from it 32, the stack pointer stops pointing here and starts pointing here at this location. And from starting from this location, we store the contents of the ninth and then the 10th register here. So this is a 8 byte memory cell. This contains the content of the ninth, and this one contains the content of the 10th register. And then this instruction stores, like this 7 is the line number. This instruction stores the content of the 11th register by adding 16. So currently I am pointing here at the bottom of this thing. If I add 8, I will if I add 8, I will start pointing here at the bottom of this 8 byte cell. And if I add 8 more, I will start pointing here. So when I add 16, I get the memory location of this place. And then I store the content of the 11th register here. So this, I get the contents of the 11th register here. That works, and the stack pointer is still pointing at the bottom of the stack, which for newbies we call the top of the stack. Okay. Little care must be taken to ensure that the arguments are stored in correct order on the stack. Remember that the store pair instruction will always push the first register to the lower address and the stack grows downward. Therefore, X9, which is the ninth argument, will be pushed onto the stack first because pre-indexing is used in X9 is actually at the highest highest address. X9, which is the ninth argument, will be pushed onto the stack first because pre-indexing is used is actually at the highest address. The 64-bit notation is used because otherwise the store pair would store both registers in just 8 bytes and 16 bytes are needed. Additionally, the printf instruction does not care for the rest of the bytes for each of the int. They are just treated as padding on the stack. Moreover, the ninth register has zeros in the upper 32-bit because the 32-bit operations such as loader 0, the upper bits, unless they are explicitly sign extended using an instruction like load register sign word. Finally, the stack must always be 16 byte aligned, which is why it is pushed down 32 bytes instead of just 24, which would actually be required to store 8 bytes of data. After the printf function is called, the ninth, 10th, and 11th arguments must be popped from the stack. If those values are no longer needed, uh, then there is no need to load them into the registers. The quickest way to pop them from the stack is to simply adjust the stack pointer back to its original value. In this case, we push 3 arguments onto the stack using a total of 32 bytes. Each argument required 8 bytes, but the stack is only allowed to grow or shrink in multiples of 16 bytes. Is that correct? Stack is only allowed to grow in multiples of 16 bytes. Therefore, all we need to do is add 32 to the stack pointer, thereby restoring its original value. Now, writing subroutines. We have looked at the conventions that programmers use to pass arguments when calling functions. These are called marshalling. Passing the arguments to their correct registers is called marshalling. Now we will examine these same conventions from the point of view of the function being called. Because of the calling conventions, the programmer writing a function can assume that the first 8 parameters are in 0 to 7. Any additional parameters can be accessed with loader register and stack pointer and then the offset. The calling function will remove parameters from the stack if necessary. Will remove parameters from the stack if necessary. If the function return type is not void, then they must ensure that the return value is in x0 and possibly x1 to 3 if the function returns multiple values and the return address will be in x30. Also, because of the conventions, there are certain registers that can be used safe freely, while others must be preserved or restored that are the poly restored registers, which are non-volatile or is restored so that the calling function can continue operating correctly. Registers which can be used freely are referred to as volatile, and registers which must be reserved or restored before returning are referred to as non-volatile when writing a subroutine function. Registers 0 to 18 are volatile. Int to integer context which has 20 numbers. Register int I. Why is the register? Try keeping I in a register. So wait, I can store integer I in a register like that. Okay, for I equals I less than 20, xi equals I. So okay, registers 19 to 20 are non-volatile. They can be used, but their contents must be restored to their original values before the function returns. Register 30 can be used by the function, but its contents must be saved so that they can be loaded into the program counter, which will cause the function to return to its caller. Register 30 can be used by the function, but its content must be saved so that they can be loaded into the program counter, which will cause the function to return to its caller. That makes sense. Although the platform register X18 has no special use on Linux system, it should be avoided because it may have a special use on some platforms, making user level assembly code that uses portable, it less portable, less portable. If portability to another operating system is not a concern, then it can be used as another volatile register. Automatic variables. In block structured high level language, JIS, an automatic variable is a variable that is local to a block of code and is not declared with static duration. In block structured high level languages, an automatic variable is a variable that is local to a block of code, okay, and is not declared with a static duration. It has a lifetime that lasts only as long as the block is executing. Automatic variables can be stored in one of two ways. Stack is temporarily adjusted to hold the variable, or the variable is held in a register during its lifetime. Makes sense. These are called automatic variables. Okay, so these things are called automatic variables. These variables are just there along for the ride till the current block has completed executing, and after it has completed executing, they will just die of vanish apocalypse. When writing a subroutine in assembly, it is the responsibility of the programmer to decide what automatic variables are required and also where they will be stored. In high-level languages, this decision is usually made by the compiler. In some languages, including C, it is possible to request that an automatic variable be held in a register. The compiler will attempt to comply with the request, but it is not guaranteed. Listing 5.28 shows a small function which requests that one of its variables be kept in a register instead of on the stack. That is cool that we can actually tell the C compiler that we want a variable to be stored in the stack. And I think only mm, things like that can be stored in there. Things like a number, things that can be contained in our register are the only things that can be stored in a register. That actually makes sense, right? That is pretty obvious. Like an integer, a double, a character, and what cannot be stored on a stack is what is it? What cannot be stored onto a stack is a string. What cannot be stored in a register is a string, but what can be stored is the address of the first character of that string. Okay, listing 5.29 shows how the function could be implemented in assembly. Note that the array of integers consumes 80 bytes of storage on the stack, and that loop control variable can easily be stored in one of the registers for the duration of the program. Also notice that on line 4, the storage for the array is allocated simply by adjusting the stack pointer. on line 14, line 4, line 14. Global do it. We have a function, global do it. What is it do it? Subs 80. Aha, what does this mean? That is getting 80 bytes of storage, and one integer takes 4 bytes of storage. That is, I have a 20 integer long array here. Then I can move into the second registers, 32 LSBs, the number 0, and then we have our loop. Compare 0 with, that is, so this is our counter. And if the contents of the second register are greater than or equal to 20, then we call done. What does done do? Done moves that variable, that counter, into the 0th register, which will be the return value of the function. Then it pops from the stack the array, adding 80 to the stack pointer, and then it returns. What does the loop do? Loop string stores the value of w2, that is the current index starting from 0 going to till 19. 19 will be the last that this thing will run at. It stores it at stack pointer at this address. What is this address? Well, this means that the address that is stored in the stack pointer, take that and add to that whatever is the value in the second register by left shifting it twice. And left shifting it twice means multiplying it by 4. So 1 will mean 4 will be added to the stack pointer, and 2 in the second register will mean 8 will be added to the stack pointer, and then the address that we get after adding to the stack pointer will be used to store this value. And that makes sense. And then we increment our counter, and then we start the loop again. This is pre-comparison loop, pre-test loop. Okay, it is critical. It says it is critical that the stack pointer be restored no matter how the function returns. Otherwise, the program will mysteriously fail at some point when it attempts to use data from the stack. For this reason, each function should have exactly one block of instruction for returning. If the function needs to return from some other location other than the end, then it should branch to the return block rather than returning directly in the middle of the function. That makes sense. That makes sense. Because the return takes care of clearing the stack. And therefore, if we have only a single return block, then we have to then the code to clear stack has to be written at only one place, and the chances of messing up are lower. Now, recursive functions. The function that calls itself is said to be recursive. Certain problems uh, are easy to implement recursively but are more difficult to solve iteratively. A problem exhibits recursive behavior when it can be defined by two properties. A simple base case, yes, a simple base case which would tell now stop calling yourself and return whatever is what we want you to return. A set of rules that reduce all the other cases towards the base case. For example, we can define person's ancestry recursively as follows. One's parent are one's ancestors. Base case. The ancestor of one's ancestors are also one's ancestors. The ancestors of one's ancestors are also one's ancestors. So for example, replacing ancestor with father. Not with father, that would not work. Ancestor would work. My ancestor's ancestor, or also my ancestor. That makes sense. Recursion is a very powerful concept in programming. Many functions are naturally recursive and can be expressed very concisely in a recursive way. Numerous mathematical axioms are based upon recursive rules. For example, the formal definition of natural numbers by the piano piano axioms can be formulated as this: zero is the natural number, and each natural number has a successor, which is also a natural number. We explicitly define zero as a natural number, and then to check if a number is a natural number, we take it and we tell that if this is specific number, for example 5, if 5 is a natural number, then its predecessor successor, that is 5 minus 1, should also be a natural number. Then we check for 5 minus 1 if that is a natural number. Then we go for 5 minus 1 if that is a natural number till we reach 8, 0. And if we see, oh shit, 0 is a natural number, then we go, booyah, 5 is also a natural number. Using one base case and one recursive rule, it is possible to generate the set of all natural numbers. Successor is like 1 plus. So if 0 is a natural number, then 0 plus 1 is also a natural number, then plus 1 plus 1 plus 1. Every integer positive, including 0, is a natural number. Otherwise, other recursively defined mathematical objects include functions and sets. Listing 530 shows the C code. This a C program that uses recursion to reverse a string. This would be fun to write in assembly. Shows the C code for a small program which uses recursion to reverse the order of characters in a string. The base case where recursion ends is when there are less than two characters remaining to be swapped. Less than two characters remaining to be swapped. The recursive rule is that the reverse of a string can be created by wrapping the first and last character, by swapping the first and last character, and then reversing the string between them. In short, a string is reversed if the string has length of 0 or 1 character, or the first and last characters have been swapped and the remaining characters have been reversed. Listing 530, line 6, checks for this base case. If left less than right, reverse a string. We have a pointer to a character that is the start of the string. Then we have left, the index of the left, and then the index of the right. And index of the left starts at 0, makes sense, and at the right starts at strlen, length of the string minus 1. And then we see, we take a temporary character temp, which stores the value of the left. And then at left we store the value of the right character, and at the right character we store the left value of the left character. We essentially swap them, and then we call a reverse at the same string but add 1 to the left and subtract 1 from the right, and this will go till either left is 0 or minus 1. Either length, the segment of the string that we are dealing with is 0 or minus 1, or 0 or like less than 0, just stupid. Okay, listing 5.31 shows how the reverse function can be implemented using recursion in AArch64. Okay, let's write this code in AArch64. Reverse string dot s. In the dot data section, we need to have a string, right, which will be stored in the ASCII format. So this is the correct order of characters, then new line at the end. Do I need anything else? Doesn't seem like it. Then I declare that there is a global thing called main, and I align the main align, line at 2. Then I define the main label. First, like every good assembly programmer, I store the frame pointer and the link register at the top of the stack by pre-incrementing it by 16 bytes. After that, I move on to do the actual task. That is, okay, first let me get the loop in the left and the right variables. We can get, and I also would need the address. So I will use the zeroth register for the address. ATRP get the address by first getting the off page address for the string and then adding the offset to the zeroth register for that string. Not in the zero, in the zeroth register, I have the address for the string that I have to work with. Now, in the first register, I have the left number, and in the second register, I have the length of the string. What is the length of the string? There was a very clever way to do that, right? Yes. Um, a byte. Yes, I can use a byte to get that. Or let's say I will use a word to store the length, and length would be equal to current location minus the string. I think that is how it is done. Now, this line at the length label, which is of 32 bits, will store the value of this length label minus the address of the current instruction, the current memory location minus the address of the string label, which is essentially the length of this string. So I can get the length. Ah, it's easy. So first I have to get the address of that label. So ADRP page address first for length page, and then add the offset to it by adding length page of, and I have to load the value into the second register whose address is also at the second register. I have the length and I have to subtract 1 from the length. So subtract and store in the second register value 1. Yep. Key. Now I have left index, I have right index. Now I need to start my loop thingy. How is my loop thingy? My loop thingy first subtracts the value of the left and right. No, it compares the value of left and right. Now, if it will branch to the end, if it is, if first is greater than or equal to the second, then it will branch to the end. And what is the end? It is Ragnarok. End first loads back the original value of stack point of frame pointer and the link register from the stack and makes the stack as it should be, and then returns all. Well, even before that, it prints the Even before that, it calls the printf function. Just calls the printf function because in the zeroth register, I already have the address of the string, so it can just call the printf function. Simply call it. Now, what happens during the loop? And at the end of the loop, I branch to the top of the loop, and also I increment. What do I increment? Yes, I add to the left and store to the left, and I subtract from the right, store to the right, one. Okay, and here comes the main body of the juice, body of the loop, which will this will swap the values. Okay, the values are in the memory. So first I have to get those in some registers, then use some temporary register to swap them, and then store them back in their memory location. So yeah, store the value in the third register. What is the value that I want to store in the third register? The first register value. Uh, the address is at the first zeroth register, and the offset is in the first register after left shifting that value two times, essentially multiplying it by 4. And same for the fourth register to get the logical shift left. So this line will get the sheet. Someone calling me my sister. Uh, this value, this instruction will get the left character in the third register. This instruction will get the right character in the third register, and the offset is in these registers. And I have to mul to multiply that offset by 4. I have to left shift those values two times, which essentially means multiplying it by 4. And then I need to swap them. For that, I will be using a temporary variable. Move into the fifth register the value at the third register, then move into the third register the value at the fourth register, then move into the fourth register the value at the fifth register. Now I have swapped them, and I am stupid. I have to load the value here. And now here I have to store them back. Store the contents of the third register at this place, LSL2. And then do the same for the right value, left shift to. This should work. And then I am incrementing and decrementing the left and right pointers, right, left and right indexes. This should work. Hopefully, hopefully, hopefully. 20, and yeah, that should work. Actually, that should actually work. And I can call printf here also before assigning anything to the. But then if I do this, I'll have to load the address again after this because printf will not keep me happy. It will change the contents of the zeroth register. So yeah, plan reverse string, put dot out, and the first problem is here, the way I am calculating the length. Okay. Well, only one way to see to check ChatGPT is this the correct way to calculate the uh, is this the uh, correct way to calculate the length of a string in AArch64 assembly on Mac? No. Well, I have to remove the brackets. Okay. I said that was just a index problem, like semantic problem. I guess I should not see that first error. Okay, that is good. Now I need to get rid of these errors. Is this the correct syntax to left shift? What is the exact error? Reverse string error. LSL or it's with optional shift of this or this. Shift of zeroth or third. Zero or third. In the book, I just saw them doing this. Yep, here. Oh, I did not provide that what I this hash. I hope that is the only problem. That is not the only problem. So is this the correct way to left shift? And the contents of a register and then use that shifted value as an offset. Yes, your instruction is mostly correct. Assembly load instruction, but there is a slight issue. The scale factor must match the size of the data being loaded. 3 to LSL correct for loading 64-bit register value. Correct for loading. Okay, so I have to say that this is a word. Static. Static. This is a word. This is the offset. This is the address. I don't think this function yet. Wait, this is the order of characters. Why did it not print for the second time? And okay, I do end here. I also call printf, but it did not print anything. Strange. Yes, strange. Strange, pretty strange. Um, okay, that is not what I expected. I'm calling printf here and it works. And then I'm calling printf here then, and it does not work here. Hmm. 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 Let me return with the um, length of the string, and I will use the sixth register to store the length of the string. And before calling printf, I will move that value to a register that is non-volatile, that is, it's 23rd register. That doesn't matter. Yep. Move the value to the 23rd register, the value at the sixth register, and then at the before the end, move the value into the 0th register, which is stored in the 23rd register. I should actually see some real output. Okay, red means error. There was some error. Echo dollar sign question mark 41. That is the length of the string. What is wrong here? Why is it not working? Shit, my font is small. Can you guys even see what I'm typing? What is wrong here? Why is it not working? I'm just so stupid. It is not very clear. You can see, you guys can see. Yeah, but I have to increase my bit rate at some point and get a better Wi-Fi. BL printf branch link printf. Uh, mm, 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 uh, word, is that it? I have to remove that, had to remove that comma. Load is getting the value here. Hmm. What is the error? Why am I not seeing what I want to see? Character, ASCII character takes. How much storage does a ASCII character take? It takes does not take 32 bytes. It takes 1 byte. Shit. It takes 1 byte. Fuck. It takes one byte. So yeah. I'm messing up here. I am actually messing up here. And and what I'm doing here is I am exchanging 32 bytes. Yeah, 32 bits of data. But the data that I want to actually swap, shit, I was going too much left, I guess. Yes, shit, that is crazy left. But the data that I actually want to swap is just 8 bits long. How can I swap 8? How can I work with 8 bits in a 64-bit register? How can I work with just 8 bits in a 64-bit register? I can left shifting values, by shifting values here and there, that might do something. No. When I'm loading and storing, the least that I can load, I can store 1 byte of data. Yes, there is a function to load and store 1 byte of data. And yeah, I got this, I got this. What is the instruction to store 1 byte of data? See, this is the instruction for AArch64 on Mac OS to store or load uh, only 1 byte of data from memory into a register. I just have to write a single B. If this works, then it works. It does not work. With optional shift of 0. Okay, get the address that way, then load like this, and then store like this. Store the byte at the next memory location. Oh yeah. I don't have to left shift. I can just add that, add one. Yeah. Um, yeah, yeah. I don't have to left shift anything. I can simply add the left and right numbers. Why? Because when adding one, I am moving forward by 1 byte, and that is the length of a character. We are pretty close, I believe. Yep. I am loading 1 byte here and 1 byte here, then moving stuff around, and then zeroth register contains the base address, and the first and the second contain the left and the right index respectively, which are being updated at the end of every loop by adding 1 to the left index and subtracting 1 from the right index. Mm, What is wrong? I'm getting the left character in the third register and the right character in the fourth register. Then I'm swapping them by storing the left in the fifth and then overwriting the left with the right and then overwriting the right with the left, essentially swapping them and then saving them back. Store byte, store byte. And then at the end, I am calling the printf function. Uh, At the end, I am calling the printf function. Maybe this is not working correctly. First starts at 0 and this starts at length -1. Which is correct. Length -1. That is the offset. This represents the offset from the start. So length -1 leaves me at the last character. Let's do it length -2 because I at the end I have a new line character. That was the problem. Oh no 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 no. At the end I have a null character. That is the problem. At the end I have a null character. That is the problem. It works now. And how long has the stream been going? 2 hours. We still have 31 more minutes at least to work here. Recursive functions. One's parents and sister. Okay, okay, okay. Zero is a natural number. Yep, yep. This is the program which we are writing in assembly, and this is the program itself. And we have written this program on our own, which is a good thing. The code enlisting weapon string reverse in C using pointers. Fucking hell. This is slightly more efficient than literal translation of the C code shown in listing 30. 3.1 is better than a literal translation. First, the string is stored in the data section instead of actually on the stack. This saves instructions that would be required to load the string onto the stack and possibly remove it. Also, the local temporary variable is not needed in the assembly implementation. Instead, both characters are loaded, then stored to the. I'm just so stupid. Yes, I can do that. Shit, I feel so stupid. Okay, instead of doing this, shit, shit. Instead of doing this, I can do this. Simply do this. Get the left character in the third and store that left character in the right and get the right character in the fourth register and then store that character in the left position and this would still work. Shit. That was pretty stupid of me. Yes, and this means that the function can use half as much stack space and will be much faster than an implementation that stores the local variable on the stack. Makes sense. The previous example used the concept of an array of characters to access the string that is being reversed. Listing 5.32 shows how this program can be solved in C using pointers to first and last characters in the string rather than using array indices. This version only has two parameters in the reverse function and uses pointer dereferencing rather than array indexing to access each character. Other than difference, It works the same as original version. Listing 5.33 shows the reverse function can be implemented efficiently in assembly. This reverse instruction implementation has the same number of instructions as the previous version, but lines 11 through 14 use a different addressing. Yes, instead of giving the base character of the string and then adding the offset, we give the actual address of the string of the character that we want to reverse or do some stuff on. On an AArch64 processor, the pointer method and the array index method are equally efficient. However, many processors do not have the rich set of addressing modes available on the AArch64. On these processors, the pointer method may be slightly more efficient. It takes a left and right pointer. If left is less than equal to right, that is, if they are same, even if they are same, what do you do? Get the value of the left in a temporary variable, then at the value of the left, store the right, and then at the right, store the left, and reverse plus minus pointer arithmetic. This is the equivalent assembly code. Yeah, oh, aggregated data types. How long is this? Aggregated data types. A target was that, and let me go to the washroom for a minute. Right back. We will complete the aggregated data types today only. Yep, me back, me back here. And aggregated data types. We will complete aggregated data types today. An aggregate data item can be referenced as a single entity and yet consists of more than one piece of data. Aggregate data types are used to keep related data together so that the programmer's job becomes easier. Some examples of aggregated data are array structures or records and objects. In most programming languages, aggregate data types can be defined to create high-level structures. Most high-level languages allow aggregates to be composed of basic types as well as other aggregates. Proper use of structured data helps to make programs less complicated and easier to understand and maintain. Less complicated and easier to understand and maintain. Okay. In high-level languages, there are several benefits to using aggregates. Aggregates make the relationship between data clear and how allow the programmer to perform operations on blocks of data. Aggregates also make passing parameters to a function simpler and easier to read. Okay, aggregate data types are blocks of memory which contain related but different data that is related to each other. Example, array, which consists of different numbers, but they are part of the same array, or objects which has different key value pairs, but they are part of the same object. Now, arrays. The most common aggregate is called what is the word aggregate mean? A whole formed by combining several separate. Okay, aggregate your children here. Okay, a material or a structure formed from a mass or fragment of pieces loosely compacted together, formed or calculated by the combination of several separated elements. Yeah, aggregate your children here. Form or group into a cluster, something big formed by adding small. Book, adding pages. By adding pages, you get a book. An array contains zero or more values of the same data type, such as same data type is like the main thing here because then each small data that constitutes the whole array is at the same con takes up the same amount of memory location, takes up the same amount s- of the offsets for each data type has have same uh, difference. The consecutive data types, the data types have the same boundary, address boundary. And I think if you want to store different data types, you can, instead of storing the addresses, instead of storing the data themselves, you can store their addresses. And then still it would take the same. The data would be stored at the same boundary, such as characters, integers, floating point numbers, or fixed point numbers. An array may also be contain contain values of another aggregate data type. Every element in an array must have the same type. Each data in item in an array can be accessed by its array index, that is the offset from the start. Listing 5.34 shows how these different listing 5.34 shows how an array can be allocated and initialized in C. Listing 5.35 shows the equivalent code in AArch64 assembly. Note that in this case, the scaled register offset addressing mode was used to access each element in the array. This mode is often convenient when the size of each element in the array is an integer of power 2. When the size of each element in an array is the power of integer 2. If that is not the case, then it may be necessary to use a different addressing mode. An example of this will be later given in section 5.3. This is my array, and this is how I traverse, starting from the 0th index, going up till 100. So I get 100 4-byte spaces in the stack. Then I initialize a counter in the 0th register by adding the putting the value 0 in the 0th register. Then I loop, start a loop, and there in the loop, I store the value in the zeroth register, which is the program counter, and the memory location which I get after calculating, evaluating this thing. What is this? This is the base address, that is the stack pointer. And to the stack pointer, I add this thing. And what is this thing? This thing means the value in the zeroth register. Left shift it by 2 times, that is multiplying that by 4 to get the proper offset. And this proper offset is added to the stack pointer to get the address of the memory where we want to store the contents of this. And then after storing the contents properly, we add 1 to the zeroth register, practically incrementing the counter. And then we compare as the value in the zeroth register reached 100, we compare it with 100 and we see if the contents of the zeroth register are less than 100, then we go back to the loop and we store again and do our thingy. Now, listing structured data. The second common aggregate data type is implemented as the struct in C or the record in Pascal. It is commonly referred to as to as a structured data type or a record. This data type can contain multiple fields. The individual fields in the structured data are referred to as structured data elements or simply elements. In most high-level languages, each element of a structured data type can be one of the base data types, an array type, or another structured data type. Fully charged. That makes sense. Okay. And then listing 5.36. Oh, 5.36 shows how a struct can be declared, allocated, and initialized in C. Listing 5.37 shows in the equivalent assembly code. Okay. 36. This is how a struct is defined in C. A struct called student, which has all this. It has an array of characters, which is 30 bytes long, 30 characters long. That is essentially 30 bytes long. Then an array named last name, which is also 30 bytes long, which also stores characters. And it has a char class, unsigned char, a thing called class, a variable called class, which stores an unsigned character. Okay, then it has an integer called grade. Now, struct student, new student. This way, I declare a variable new student, which will copy this, and what does this do? String copies this string at this place, and this copies this string at this place, and new student dot class is this. What grade is this? Okay. Here, tr here must be taken using assembly to access data structures that were declared in higher level languages such as C and C++. The compiler will typically pad a data structure to ensure that the data fields are aligned for efficiency. On most systems, it is more efficient for the processor to access word-sized data if the data is aligned to a word boundary. Some processors simply, okay, on most systems, it is more efficient for the processor to access word-sized data. That makes sense if the data is aligned to a word boundary. Some processors attempt to do so will result in an exception. Some processors attempting to do so will result in an exception. The assembly programmer must somehow determine the relative address of each field within the higher level language structure. One way this can be accomplished in C is by writing a small function which prints out the offsets to each field in C structure can be accomplished in C by writing a small function which prints out the offsets to each field in the C structure. The offsets can then be used to access the field structure from the assembly language. Another method for finding the offset is to run the program using a debugger and examine the data type. And this is the way to Yep, this is the way to declare that. I have a string called Sam and a string called Smith. Then in the text, I have something EQ which is S first name, which is 0, stores the value 0. What is EQU? Then I have a label this string names which stores this. And then I have a label S class which stores 30. Okay, S class which stores 30, and then I have a grade which stores 64, then size which stores 68, and size aligned which stores 80. Function then I store the frame pointer and the linker register onto the stack, not by adding subtracting 16 bytes, but actually 32 bytes, which is an overkill. Literally, yep, that is double the thing that I need. And then I store the contents of the 19th register. This callee saved has to be saved. Callee me has to be saved by me. The contents of no, then I store the contents is of the that 19th register at the stack pointer with an offset of 16. Okay, struct student new student. Okay, how do I declare a new struct? First, I subtract from the stack pointer the hash, hash, hash size align. Okay, these are just labels which I can directly use here by using hash and then the label name. So at this point, I have 80 bytes of storage in the stack. Then I move the stack pointer to the 19th register, the lowest bit of the stack pointer to the 19th register. Then I add first name to the 19th register and store that new address in the 0th. Then I get the address of Sam in the first register, and then I stir copy, call stir copy. What will this stir copy do? It will copy the contents of uh, it will copy the contents of the string whose first address is in the first register into the address at the 0th, into the location whose address is in the 0th register. Then I call stir copy, and then I do the same for the last name. Okay, stir copy, and then I move number 2, just randomly number 2 into the first register. Then I store byte from this because byte, single byte into the 19th register plus class. Yup, because this is unsigned character, right? So it takes only a byte to be stored. I store 2 into the first register, and then move 2 into the first registers, and then store a single byte from the first register at the place where I am supposed to store class. And then I move 88 into the first register and then store that 88 into the place that where the grade is supposed to be stored. And then I delete the structure by essentially popping it and getting the stack pointer um, back to where it was before I subtracted this value from the stack pointer. That makes sense. That is okay. Array of structured data. It is often useful to create arrays of structured data. Arrays which contain structured data. For example, a color image may be represented as a two-dimensional array of pixels. As a two-dimensional array of pixels, therefore an array must contain another array, which where each pixel consists of three integers and yeah, which specify the amount of red, green, and blue that are represented in the pixel. Typically, each of the three values is represented using an unsigned 8-bit integer. There is a single byte. Imagine processing software of 10. Uh, Image processing softwares often add a fourth value, um, alpha, specifying the transparency of each pixel. Transparency of each pixel. Okay. Listing 5.38 shows how an array of pixels can be allocated in and initialized in C. The listing uses malloc 5.38. Okay, it is about to be time. So today we will conceptually understand what the heck is going on, and tomorrow we will write the program for storing in a structure like this program, and then initializing an array of structured data in C as improved initialization in C. Yep. And then chapter summary, and then we can just move on to the exercises, and the chapter will be finished. Quite a few questions, and then abstract data types. We are reading about aggregated data types here. Eh, I think that should be enough. Wait, this the listing uses the malloc function from the C standard library to allocate storage for pixels from the heap. Okay. C section 1.4 heap. Heap is like below the stack. Below the stack, there is some empty space between heap and the stack, and then below that, there is the stack. Note, the code uses the size of function to determine how many bytes of memory are consumed by a single pixel, then multiplies that by the width and height of the image. Listing 5.39 shows the equivalent ARM assembly code, and note that the code in listing 5.9 is far from optimal. 5.39. This is the way. This is a pixel unsigned character, that is a single byte to store red, green, and blue. Okay, and then a structured pixel. We have a structured pixel, a pointer called image that will point to a structured pixel, to a data structure containing this thing. And how long will that be? That will be malloc into, we'll get, now inside this we have to enter the number of bytes that we need. So the size of this will return three, 3 bytes, and because we are using 3 bytes to store these, and then multiply that by height and multiply that by width. If image equals to null, that is we did not got any pointer, then printf enter to a file standard error, formatted printf to the standard error out of memory. Okay, but if we do get a pointer to a pixel, then what do we do? For int I less, we traverse, we loop through the height and width and initialize everything to zero somehow. Yeah, every, every pixel to zero, and the image would be dark, complete black. And then we free that memory location which we got in malloc, then essentially deleting the image. That is okay, makes sense. As far from optical, it can be greatly improved by combining the two loops in one loop. It will remove the need for multiplying on line 31 and addition, and will simplify the code structure. Okay, yes, the pointer. Okay, this is the offset, and each offset is unique to every pair of I and j. Okay, and the maximum it can go is the maximum amount of memory that we have. That is okay. Uh, then we write the same thing in assembly, which we will be writing. Like I said at the beginning of the stream, we cannot compromise quality, and I don't think I will be able to write the best quality assembly code right now. So therefore, we will be continuing from this part in tomorrow's session. We will be writing assembly code for two things. First, for this, how this is the actual assembly code, how to allocate a structure in assembly language, and then this, how to allocate array of structure in the assembly language. That would be cool. Then there is an improved version of the same thing. And then we will begin doing the questions. Hey, that was good extreme.